This homework example is similar to an example we did in class with the coffee cup. I did have some questions about that coffee cup example, so I think we'll take our time and we'll go through this one, and hopefully this is going to clear up some issues. Mostly the questions I got were about the cosine versus sine and the weight components. So we have a person sliding down a steep water slide. The friction between the person and the slide is negligible, so we're not worried about friction. Part A, draw the free body diagram for our person going down the slide. So we'll start with our free body diagram. I'm going to draw a steep slide. I'm going to draw the ground. This is 80 degrees. I'm going to put a person on the slide. Okay, now we have to draw the forces. Let's draw the easiest force first. We know that the earth pulls straight down on the person. So there's the weight vector W. That one's pretty straightforward. Next, we have to do the normal force. We know normal forces are perpendicular to the surface and out of the surface. We need a line that's perpendicular to our slide and pointing away from it. So our normal force has to put this way. Just to confirm, if you like the idea of looking at something like it's just sitting on a table, if we put our line horizontal, then our normal force is perpendicular up. Okay, so there's our normal force. I'll draw that one out. There's our normal force N. Whenever we draw our free body diagrams, we have to choose a coordinate system. We're going to choose a coordinate system so that the x-axis is parallel to our surface or parallel to the acceleration. Our person is sliding down the water slide. So the acceleration is down the hill. We're going to take our coordinate system so that the x-axis is down the hill parallel to the acceleration. You don't have to take it this way. If you took your x and y axis this way, your work would be legitimate. You could do that, but you see you'd have components of your acceleration. The math would just get a little bit tanglier because you'd have to deal with components. If we take our coordinate system this way, then all of the acceleration is in the x and none is in the y. That's why we tilt the coordinate system. Okay, so we'll put a little tip here, choose coordinate system, and this is how we often do things. So that x is parallel to A. This just makes the math easier. Okay, so there's our little tip and our method of doing things. So what this means in practice, when we come to our equations, the x component of the acceleration is going to be the whole thing. The y component is going to be 0 because our person doesn't move up or down relative to that slide or perpendicular to that slide, only parallel. Okay, so there's our free body diagram. There's our coordinate system. We know that we have to put our vectors into their components. If we look at the normal force, we see that that's all in the y direction because it's all perpendicular. Our weight force, not so much. That points straight down. So that's a little bit x and a little bit y. Those components can be tricky to draw. So why don't we go through all the details of how we find those components again? I know we did it in class, but let's give it another go, just in case you had some questions and you wanted to see it again. So I'm going to put my person on the slide. I'm just going to redraw my components or redraw my forces. My normal force was perpendicular out of the plane. There's the normal force. And my weight vector, I'm drawing it nice and big because we want to have a good picture. My weight vector points straight down. That's W. Let's put in the coordinate system because the coordinate system is really important. There's x, there's y. Now the next thing I'm going to do, just to really visualize where I have to put my components, is I'm going to trace my coordinate system right on top of my vectors. So my y component, my y coordinate system is all perpendicular to the plane. That's my y-axis. My x-axis is all parallel to the plane, straight downhill. There's my x-axis. So if we look at this, we see that n is perfectly aligned along the y. So my n is all in the y direction. Why don't we even get that bit of information down? So n, all in y direction. What that means is that my y component of n is plus n. and my x component of n is 0. Okay, we've been doing that one for a bit. That's okay. Our weight, not so much though. You see that my weight is not parallel to y or parallel to x? That means our weight has an x component and has a y component. For some people, that's easier to see if you twist your paper so that x and y look the normal way. If your x looks like this and your y looks like this and your weight is over here, that helps you see that your weight does have an x part and a y part. Part of it is parallel to the hill and part of it is perpendicular to the hill. So the next thing we have to do is draw those components of the weight vector. To draw those components, we might remember how we drew components way back in chapter 3. Okay, so you can make a rectangle out of your vector. If you make a rectangle out of your vector, that will really help you get your components straight. So I've made my rectangle here. My x component of my weight vector is the part that lies along the x-axis, and it only goes as far as my weight vector goes. So my weight vector goes over this far. That means my x component goes over this far. Okay, so here's my x component, wx. My y component goes along the y-axis, and it only goes down as far as my w vector goes. wy. So there are my x and y components of my weight vector. I'm going to tilt my paper back now. And you see that nothing has really changed. We're just looking at it a bit differently than we have so far. Okay, my x component is down the hill. My y component is perpendicular into the hill. Why don't we make a note of those things? Wx parallel to x, or parallel to the plane. Wy parallel to y, which means it's perpendicular to the plane. The x component goes down as far as w in the x direction, the y goes down as far in the y direction. Okay, we know we need to use our trig to find our components, which means we need to use sine and cosine. I know particularly if you did physics in high school, you're really used to using cosine with the x component. You've got to be so careful with your vectors to make sure you're using the right trig identity. So what I'm going to do is let's have a look at this triangle right here. So I've got it isolated by covering most of the diagram. So we're going to look at this triangle right here. As I look at this triangle, I recognize that my weight comes down, so it's vertical. This is horizontal, so this has to be a right angle right here. Okay, that's got to be perpendicular because weight is vertically down. My ground is perpendicular to that. It's horizontal. I know all the angles in a triangle have to add up to be 180 degrees. So this angle in right here has to be 180 minus 90 minus 80. That means this angle is 10 degrees. Okay, hopefully that's really clear. So this is a triangle. These three angles have to add up to be 180 degrees. Okay, we often label this angle in the diagram. It's just a standard way of doing it. We label the angle between the y component and the w component, or the w vector. So now I want to look at my x and y coordinates, my x and y components. The x component is down the hill. The y component is perpendicular to the hill. X and y are always perpendicular. This is a 90-degree angle. Okay, I want to label this, but I don't want to completely overwhelm the diagram. Okay, so these have to be perpendicular. That means these two angles have to add up to be 90. That means this one is going to be 90 minus 10 degrees, or 80 degrees. So our angle in here has to be 80 degrees. So overall, when you have things on an inclined plane, you're going to draw your vectors. Your weight's going to point straight down. The x component is parallel to the hill. The y component is perpendicular and into the hill. And this angle are going to be the same. Probably that's just going to be a result you remember, but it is good to see where it comes from at least once or twice. Okay, let's get started on should we use sine or cosine for our angles. Well, if we look at our y component, we see it is next to the angle or adjacent to the angle of 80 degrees. So my y component is adjacent to my angle. It means for my y component, I have to use cosine. So the magnitude of my y component is going to be the magnitude of my weight times cosine 80 degrees, and that's because it's adjacent. My x component, I could draw it here or I could draw it down here. Both are legitimate. My x component is opposite my angle of 80 degrees, so for my x component I have to use sine. Okay, so that's the explanation about how we get the components we get. Let's just come on back to our diagram on the previous page, and let's label those components on this diagram. So I'll put in my x component right here. Wx comes down the hill. Wy is perpendicular into the hill. And this angle is also 80 degrees. So when you draw your free body diagrams, this is most likely what they're going to look like. Next step we typically do is we make a table showing what our components are. Let's do that part next. So the two vectors we have are the normal force and the weight force. We want to list the x and y components. In the x direction, the normal force is 0, and it's all in the positive y direction. In the x direction, our Wx points down the hill. Our positive x is down the hill. So our x component is positive because it's in the positive x direction. On the previous slide, we showed that the x component is opposite the angle, so we had to use sine of 80 degrees. For our y component, it points into the hill. Positive y is out of the hill, so into the hill is negative. Our y component is adjacent to our angle, so we have to use cosine here. And then down here on the bottom, we might just make a reminder for ourselves that the magnitude of the weight vector is m times g. All right, so part A, all done. We've done super. Part B, find the magnitude of the normal force. The normal force is in our y column. Let's do Newton's second law in the y direction. So part B, what is the magnitude of the normal force? Notice that it asks for the magnitude. That means we don't have to write it as a vector this time. So the sum of the forces in the y direction is the mass of the person times the acceleration of the person in the y direction. In the y direction, we have normal minus w times cosine theta. Oops, I was going to say theta, but I'll stick with the 80 degrees. Cosine 80 degrees. Mass times acceleration in the y. The y direction is this way. Our person goes down the hill. The person doesn't go perpendicular to the plane, only parallel. That makes the y component of acceleration 0. Okay? That's why this coordinate system is nice. It lets us put a 0 in here. So n equals w times cosine 80 degrees. W is m times g. Put our numbers in. Our person has a mass of 70 kilograms. G is 9.81 meters per second squared. Then we're multiplying by cosine 80 degrees. The magnitude of our normal force is 119 newtons. Okay, so it took us a long time. You'll get quicker at this as you get more practice. Part C, find the acceleration of the person. Well, the person is sliding down the water slide, so the acceleration is going to be down the water slide. We drew that in our picture. That's the x direction. So we're trying to find the acceleration, which is in the x direction, or the x component. That means we should look at the x information. So part C, what is the acceleration? Sum of the forces in the x direction is mass times the acceleration in the x direction. In the x direction, we have w times sine 80 degrees equals mass times the acceleration in the x direction. And the acceleration in the x direction is the weight. Remember that was, oh, hang on. M times g times sine 80 degrees equals m times a in the x direction. Notice that you have your mass on both sides of the equation. So let's just save ourselves a step on the calculator and divide both sides by m. And we see that our acceleration in the x direction, which is the whole thing, is equal to g times sine of 80 degrees, 9.81 meters per second squared times sine 80 degrees. So our acceleration is got a magnitude of 9.66 meters per second squared. It is completely in the positive x direction, so we can label it with an x hat. We could also say down the hill. That would also be an acceptable answer. Okay, so let's do one more example of something sliding down a hill. And let's take our skeleton racer, John Montgomery. Let's say he's sliding down a track, which is inclined at an angle of 75 degrees. The coefficient of friction is 0.01. What's John's acceleration? So this one is very much like our water slide example, but now we have friction in the picture. John is sliding down the track, which means he's in motion, and our friction is going to be kinetic friction. Okay, so we'll start with a free body diagram. We'll draw the hill, pretty steep again. We'll put John on the track. I think this time I'm just going to use a dot rather than try and draw a person. Let's get our vectors in here. The weight vector points straight down. The normal vector points straight out of the surface. There's the normal. Here's our weight. The friction, so John is sliding down the hill. His acceleration is in this direction. The friction opposes the motion, so the friction is up the hill. And we said because he's sliding, that has to be kinetic friction. We need to put the components of our weight vector here. So we'll show our x and y coordinate system. Positive x down the hill, positive y perpendicular to the hill. Our y component points into the hill. There's wy. And our x component is parallel to the hill. wy, wx. This angle is 75 degrees. This angle is 75 degrees. Okay, so there's our free body diagram. Let's sort out all of the components of our forces. Got the normal force, I've got my friction force, and I've got my weight force. I want to get my x and y components. The normal force is only in the positive y, that's plus n. My friction force is only in the negative x, so minus fk. I might remember in this table that that's mu k times n. No y component here. My x component of weight is down the hill, so it's positive x. It's opposite my angle, so it's plus w times sine 75 degrees, or plus mg sine 75. Remembering that weight is m times g. My y component is into the hill, that's the negative y direction, minus w. It's adjacent to my angle, so I have to use cosine, so minus mg cosine 75 degrees. Okay, free body diagram, coordinate system, components of forces. John's acceleration, he's going down the hill. Our acceleration is all in the x direction. None of it is in the y direction. We'd like to find his acceleration in the x direction. That has all of these forces in it. I see that I've got a normal force in my x direction. That tells me in order to find my x acceleration, I'm going to need to know my normal force. I think I'm going to go ahead and find my normal force first, then I'm going to come back to my x equation. Okay, so that's my plan. So let's get into our equation in the y direction. So Newton's second law in the y direction. Sum of the forces in the y direction is the mass of John times John's acceleration in the y direction. In the y direction, I've got plus the normal, minus mg cosine 75 degrees equals mass times 0. John does not move perpendicular to the plane, he only moves parallel, so his ay is 0. N equals mg cosine 75 degrees. John's mass is 81.8 kilograms. Let's not fill in those numbers just yet. I got a feeling that that m is going to cancel. If you were a numbers person, you might fill it in. 81.8 times 9.81 times cos 75. So if you like numbers, you're probably going to find that n equals 207.7 newtons. If you're a symbols person, you'll work with just symbols. Okay, let's next go to our x equation. So we'll do Newton's second law in the x direction. Sum of the forces in the x direction is mass times acceleration in the x direction. In the x, I have minus mu k times n plus m times g times sine 75 degrees equals mass times acceleration in the x. My normal force, so I can put in numbers here at this step and solve for ax. If you do that, it is completely legitimate, no problem, you'll get the right answer. I'm going to fill in symbols for my normal force. Minus mu k times m times g times cosine 75 degrees plus m times g times sine 75 degrees equals m times a times x. The reason I'm doing this in symbols right here is because once in a while you're going to see a problem and John's mass wouldn't be given. If that were the case, what you would do is you would work through your problem. Every time you wanted to put in 81.8, you wanted to put in a value for mass, you'd just leave it as a symbol. And then you'd see you'd get to a step where you had an m in every single term. So you could divide all terms on both sides by m, and those m's would cancel. See that it doesn't matter what John's mass was? So ax is minus mu k times g times cosine 75 degrees plus g times sine 75 degrees. You can take your g outside if you want, or you can just pop your numbers in. Mu k is 0.01 times 9.81 meters per second squared times cos 75 plus 9.81 meters per second squared times sine 75. Put all that through the calculator, and what we get is 9.45 meters per second squared ax. All of our acceleration is in the x direction. It's all down the hill, so it's positive x direction, so we put an x hat on there. So there's another hill problem for us.